Hello, and welcome to today's lesson, which will be on upper and lower bounds in calculations. First of all, I do apologise for the 2-week delay. I've been having some technical issues which hopefully are all resolved now. So, let's start at the deep end today. If I can work my technology. I have a question here. A rectangle has side lengths of 20 centimetres and 30 centimetres, accurate to the nearest 10 centimetres. What is the upper bound for the area of the rectangle, and what is the lower bound? So, as usual with one of these written questions, we are going to highlight the important information. First of all, we're dealing with a rectangle with side lengths of 20 and 30 centimetres. And they are accurate to the nearest 10 centimetres. And we are being asked first the upper bound and then the lower bound. And how do we actually go about working this out? Well, it might be a good idea. Let's say we've got, there we go, length 1 and length 2. So length 1 will say is 20 and length 2 will say is 30. It doesn't matter, we could have done it as 30 and 20. This is typical WOOLOG without loss of generality, which basically means we can make that distinction without losing any integral part of the problem, i.e. that distinction is just 1, but it represents all of them. Anyway, I'm rambling, sorry. So, now what we can do, we've defined L1 and L2, we can find the lower bounds and the upper bounds of each. So the lower bound of length 20, well, what's the accuracy? First of all, we've highlighted that it's the nearest 10 centimetres. So this is accurate to the nearest 10. So if it's accurate to the nearest 10, the lower bound is going to be 20 minus half of 10, which is 20 minus 5, which is 15. And we've given up. Okay, I'll write that in a sec. We really have given up writing today. Cool, helpful. I can't get my pen to work. There we go. Do apologise. The upper bound, same thing, except it's 20 plus 10 over 2. 20 plus 5 is 25. Oh, we've gone again. I don't know why my pen is being so dodgy today. This is going to make things quite hard. Similarly, 30, I'll do it quick. Oh no, there we go, too late. The lower bound is 25 and the upper bound, is 35. Again, you can work out how I got there myself. But then what do we do with this information? So, if we wanted the upper bound of the area, obviously the area is length times width, or L1 times L2. But we want to make that as large as possible within the bounds that we have here. Now, how do we make that as large as possible? Well, we want to multiply two numbers that are each as large as they can be. In this case, we want to multiply the two upper bounds together. We try that, and we're going to get 25 times 35 for the area. And I'll just get my trusty calculator up. That gets you an area of 875, obviously, centimetres squared for the upper bound. And that's correct. Well done us. Similarly, the lower bound is just multiplying two numbers together that are as small as possible, because that will give us the smallest result. So that's going to be 15 times 25, which equals 375, or would do if I were allowed to write that. So this is interesting. Obviously, we've got a rectangle. We're told it's got 20 centimetres and 30 centimetres lengths, accurate to the nearest 10 centimetres, and we actually find the area can range from a mere 375 centimetres squared to 875 centimetres squared. And that's quite a lot, right? That's 500 centimetres squared in range. Why is it so vastly different? That's because of how inaccurate R20 and R30 are. Obviously, they're only accurate to the nearest 10 centimetres. They're not very accurate. If they were accurate to the nearest 1 centimetre, we'd be doing 19.5 times 29.5, which would be significantly less drastic. It's only 575 and a quarter centimetres squared, and similarly it would be 20.5 times 30.5, which I cannot put into my calculator, which is 625.25. You get a much smaller range. So this is why accuracy matters, because the more accurate something is, the more precise and the more accurate our later results will be. See, multiplying two relatively inaccurate results gives us a vast span of a potential result, and that makes it hard to actually work with. So, to calculate the upper bound, as we saw, I multiplied the upper bound by the upper bound. And to calculate the lower bound, I multiplied the lower bound by the lower bound. This makes sense if you stop and think about it. If I'm multiplying 15 by something, and my range is from 25 to 35, the smallest I can get is if I use the 25. Anything bigger is going to be more lots of 15, and therefore it will be bigger. Similarly, if I'm multiplying by 25, my lower bound for L2, and the range of what I can multiply by is 15 to 25, anything bigger than 15 is going to be more lots of 25 than 15, so 15 is going to give me the lowest result. And a similar argument works for the upper bound. So I've typed out this useful chart. This is basically how to calculate upper bounds or lower bounds for each of the operations. So if you're adding or multiplying, you use the two that are the same as the result you want. So if you're going for the upper bound, it's upper bound plus upper bound, or upper bound times upper bound. Similarly, lower bound is lower bound plus lower bound, or lower bound times lower bound. So basically, if I'm asked to work out the upper bound and I know what operation I'm doing, all I need to do is check this table to see which of the two numbers I want to use. Now, sometimes you will be given calculations that ask for more than two numbers. And if I want to do that, it's quite simple. I can just break it down. So say I've got three numbers to multiply and I want the upper bound. Well, first of all, I know that the upper bound of that, well, I know that the let me start again. I know that the numbers, we'll call them N1, N2, and N3. Now, if I wanted just N2 times N3, I know how to calculate the upper bound of that. I just take the upper bound of both of those. So we've got the upper bound there. And then all of a sudden, my overall upper bound is N1 times an upper bound. And that's good. I want an upper bound times an upper bound. So I can just take the upper bound, hopefully, there we go, of N1. Nice and simple. So if you've got 3 or 4 or 5, or just more than two numbers, just break it down, take one pairing, work out how to make the upper bound of that, or the lower bound, depending on what you need. Work out what you need to make that, and then make it that. So here we go. This, somewhere down here, is a question for you. This is a very hard question, so pause the video for as long as you want. I will talk you through it first though. So a cuboid has a volume of 8.4 centimeters cubed, correct to the nearest 0.1 centimeters cubed, and side lengths of 40 millimeters, 55 millimeters, and X millimeters, and all of those are correct to the nearest 5 millimeters. So obviously I will highlight my nearest degrees of accuracy as well. And then it says, show by calculating the upper and lower bounds of x that x equals 5. Obviously, when it says x equals 5, that is x equals 5 correct to the nearest 5 millimeters. So what you're probably going to do is when you calculate the upper and lower bounds, you'll find that both values correct to the nearest 5 millimeters are going to be 5. That is what it's asking you to do. So feel free to pause the video and have a go at that. Okay, once you've done that, let me talk you through. So the first thing to notice is that we've got a volume in centimetres cubed, but all of our side lengths are in millimetres. So let's start. The easiest place to start is converting all of them into either millimetres and millimetres cubed or centimetres and centimetres cubed. I'm going to choose to turn the volume into millimetres cubed. So 8.4 centimetres cubed is, here we go again. Eventually it will let me write. Is it going to be any better like this? Oh, God. Sorry. I'm going to get a new stylus. Yeah, this is unusable, sorry. Oh, there we go. It's 8,400 millimeters cubed. Centimeters is times 10, so millimeters squared is millimeters times millimeters. To get that into centimeters times centimeters, it's times 10 times 10 is times 10 squared is times 100. Therefore, to get millimeters cubed into centimeters cubed is times 10 cubed or times 1,000. Sorry, to get centimeters cubed into millimeters cubed is times 1,000. So, and we know this was accurate to the nearest 0.1 centimeters cubed, which means it's now accurate to the nearest 100 millimeters cubed. I'm going to put that in brackets. And our side lengths we know are 45 millimeters, 55 millimeters, and x millimeters. So first, it's telling us what to do. It wants us to calculate the upper and lower bounds of x. So let's start. A good way to start is always label. I'm going to label with text to save my stylus having to do any more work than is necessary. We'll start with the upper bound. I'll just press the enter a couple of times. Okay, so how do we calculate the upper bound of x? Well, what is x? First of all, we've got the volume of a cube times the side lengths. We'll call them L1, L2, and x. Sorry, it's capital X. And how are all of these linked? Well, the volume is, oh, there we go. The volume is L1 times L2 times x. Well, in a minute, I'll actually put that in. Okay, so that means that x, little bit of algebra, will be covering that in my next lesson, so don't worry if this bit doesn't quite make sense. But x equals the volume divided by L1 times L2. That's just basic rearranging of the formula. Again, I said I'll cover that. I'm moving on to algebra next week, so do tune in then. Okay, so if x is the volume divided by L1 times L2, and we want to get the upper bound, if you look at the lovely list of formulas, we'll find that that upper bound is going to equal the upper bound divided by the lower bound. Magic, obviously, if you take a large number and you want to leave it as large as possible, you divide by the smallest thing possible. So, the upper bound of V is our volume, which is 8,400 millimeters cubed, correct to the nearest 100 millimeters cubed. That means 8,400 plus 100 over 2, which is 8,450 in total. Oh, you've completely, there we go. So we're going to have 8,450. But now, we want the lower bound of L1 times L2. And this is multiplication. We know that the lower bound there is just going to be equal to the lower bound times the lower bound. Nothing too strenuous there. So the lower bound of L1, which we will say is the 40 millimeter length, nothing, it's correct to the nearest 5 millimeters. Oh, so that was not supposed to happen. That's better. Correct to the nearest 5 millimeters, so it's 40 minus 5 over 2. It's 40 minus 2.5. It's 37.5. And L2 similarly, 55 minus 2.5 is 52.5. Or will be, when I'm allowed to write that. Plug that into your calculator and you'll get a result for the upper bound of x, which I will just very quickly work out on my own calculator here, which is 4.29. We'll leave it there. It's several more decimals after that, but that's good enough for us. Bear in mind, we want it closest to the nearest 5mm. As we can see, 4.29 correct to the nearest 5mm. Well, it's going to round up to 5mm. It's greater than 2.5. So if that is 5 to the nearest 5mm, we need to show that the lower bound is also 5 to the nearest 5mm. So again, labelling. Do the lower bound. Now we know the formula, they're the same as last time. X is V over L1 times L2. This time the lower bound is going to be the lower bound divided by the upper bound. So to get the upper bound of the multiplication on the bottom, we're going to do upper bound times upper bound. Okay, back to the point where I have to use my stylus. The lower bound of the volume is 8,400 minus 50 is 8,350. Oh, it worked first time, unusual. And then the upper bound of the two lengths that we're dividing by is their upper bounds multiplied together. It's 40 plus 2.5, which is 40. There we go, 42.5 times 55 plus 2.5, which is 57.5. And then we just go and put this into our calculator. So 8,350 divided by, and then 42.5 times 57.5 equals 3.42. 3.416, the 6 rounds up to 2. And as we can see, this is also greater than 2.5, so to the nearest 5mm, this is going to round up to 5. So we've shown that the lower bound of x is 5mm to the nearest 5mm, and the upper bound of x is 5mm to the nearest 5mm. And given that we were told initially that x was correct to the nearest 5mm, x has to equal 5 correct to the nearest 5mm. This is not a particularly useful result. Obviously, x can't actually be 5mm. It's far too big a suggestion. But it goes to illustrate how to do calculations with lower bounds and upper bounds. So in that regard, it's fine. As a problem, it's great. As an actual example, it tells us absolutely nothing other than accuracies can be a bit trash. So as I already said, my next video will be on the basics of algebra. I look forward to seeing you then. I intend to do it next week unless more rampant technical issues occur. But until then, just keep up the good work.